video is for Math 112. This is for section 1.2, which is an introduction to trigonometric ratios. And so trigonometry is all about the relationship between the angles in a triangle and the sides of that triangle. So let's take a look at this diagram that we've got in the textbook. This is page 13. And I've got it drawn like this. Here's our right angle. So the longest side across from the right angle is the hypotenuse. I've put an angle, and in trigonometry it's customary to use the Greek letter theta, which looks like this, okay, to represent an unknown angle. It's sort of the companion to the x that we use throughout algebra. Okay, theta is often used to represent an angle. This side is the side that is adjacent to the angle, and this side over here is the side that is opposite the angle. Okay, so that's the fundamental starting place for some of these ideas about trigonometry. Is the right triangle with the hypotenuse across from the right angle. The side opposite the angle that we're interested in is called the opposite side, and the side adjacent to that angle is called the adjacent side. There are other ways to approach trigonometry. I've kind of explored some of them, or I've read about some of them, you know, in the ancient approach to trigonometry was more about circles and chords in a circle, you know, sort of things of this nature, where your angle theta was in there and some length over here, L, would be calculated. But modern trigonometry is frequently based on the right triangle, and then also something that we'll talk about, I think it's in chapter 2, which is trigonometry on the coordinate axis. Okay? And so in chapter 2, we'll look at angles as they rotate away from the positive x-axis, and our angle will be there. And we'll talk about that more in chapter 2. I'm going to start off with right triangle trigonometry, and then we'll expand those other considerations as well. Because that angle that I just drew, actually, is an obtuse angle, and it wouldn't exist in a right triangle, right? In a right triangle, once this angle is 90 degrees, these angles both have to be less than 90 degrees. Okay, so in the right triangle, our definitions here are the sine of the angle theta is defined as the side opposite the angle over the hypotenuse. So this is why they're called trigonometric ratios, is because they're ratios of the sides. Okay? The cosine of the angle is defined as the adjacent side over the hypotenuse. And then the tangent of theta is defined as the side opposite over the side adjacent. And so I'll write out the full words for these. Sine, cosine, and tangent. The SIN, COS, and TAN are just abbreviations for sine, cosine, and tangent. So these are the definitions. Sometimes people I'm not going to ask you to memorize them. These will always be available to you when you're test taking. If you move on in mathematics, you might find yourself in situations where you have an instructor who has expected you to memorize these. I'm not going to do that. I think that it can be helpful to memorize them, but I'm not going to force that on us. And so this is all sort of a lead up to telling you about this mnemonic device that people frequently use, TOA, and that implies that the sine for an angle is the opposite over the hypotenuse. The cosine for the angle is the adjacent over the hypotenuse. And the tangent for an angle is the opposite over the adjacent. So that's one way that you can memorize this if you want to. For some reason, I memorize this spatially, where I see the sign. I always remember them in this order, and the sign going opposite over hypotenuse, then adjacent over hypotenuse, and opposite over adjacent. That's what worked for me. I'm not going to, try to figure out why that worked for me, or, try to force that on other people. But that's how I approach this, and that SOHCAHTOA can sometimes be helpful. So those are the definitions, and that is a big deal in mathematics, because once you define something, then you can build on it. Okay, so these are definitions, and they're calculations. Really, the whole point of this is to establish these values for particular angles, and then save yourself the trouble of recalculating them later on. Okay, that's why our calculator has been pre-programmed. Well, it's been programmed really with an algorithm for calculating these values that we talk about in calculus class. I'll talk more about that as we look at these values. Let's see here. So let's look at some examples in the textbook. Let's see here. Well, let's go ahead and work on the problems that start on page 19. Let's see here. I think maybe I'll move all of this stuff over to here. So here's our triangle. There's theta. There's the side opposite. There's the side adjacent. There's the hypotenuse. Oh, one thing I didn't mention in the textbook is that obviously if you move the angle over to here, then this will be the side opposite, this will be the side adjacent, the hypotenuse stays the same. And then I'll put the definitions down here. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and then the tangent is opposite over adjacent. But I'll get these out of the way, and we can look at problem 2 on page 19. Let's see, we've got kind of a long, skinny triangle. Got a right angle there. Our theta is up here. This is the square root of 2, and this is 5. And we want sine theta, cosine theta, and tangent theta. Okay, well, you can see we're missing this side down here in the triangle. So, if you're not familiar with Pythagorean's theorem, the Pythagorean theorem, which was known to a lot of different cultures all over the world, even before the time of Pythagoras, but he's the one, his group of Pythagoreans were well known to work with this and also to demonstrate its validity. Okay, a lot of cultures worked with it, but I think that Pythagoras was probably one of the first, or the group of Pythagoreans were the first to prove its truth. All right, so that means, now it's vitally important. This is one of the, this is really an important concept in right triangle geometry and trigonometry. A and B have to be the legs of the right triangle. Number one, it has to be a right triangle. I've seen people try to use this formula for a triangle that doesn't have any right angles in it. Can't do that. Okay? So that's number one. This is only true for a right triangle. Next, A and B have to be the legs of the right triangle, while C is the hypotenuse. It doesn't matter which one's A and which one's B, okay? But what is very important is that C is the longest side of the triangle, which is the side across from the 90-degree angle. Okay? So, given that information, we can start this out. Let's say I'll call this A down here. So then we would say A squared plus square root 2 squared equals 5 squared. Okay, so now we've got everything set up, and we can go ahead and solve for the value of A. So this will be A squared. Square root of 2 squared is 2. Okay? I mean, you can do that on a calculator, but that also goes back to the definition of a square root. All right, now let's get the A squared by itself. Subtract 2 on both sides. A squared is 23. A is the square root of 23. Okay. I suppose that we could do approximations here, but most of the quantities in this section are expressed in terms of square roots, and so I'm just going to leave this as square root 23. Now, once we have that, we can say the sine then is going to be square root 23 over 5. The cosine is going to be square root 2 over 5. And the tangent is going to be square root 23 over square root 2. You know, you can combine those like this. Any one of those answers is correct. So that's really what this section is mostly about. Number one, being competent in using the Pythagorean correctly to find the missing side in a triangle, and then just this practice of identifying sine, cosine, and tangent for an angle that lives in a right triangle. Okay. Let's see, let's do another problem here. I'm going to put that right triangle back up there. There we go. What else do we have here? Well, problem 4. We've got a triangle that looks like this, where this is 3, this is 7. Our angle theta is down here. And so to find this side, I'll call it C. Then we say 3 squared plus 7 squared equals C squared. 9 and 49 is C squared. So that looks like it's going to be 58. And so C will be the square root of 58. Okay, let's see here. Now notice I've erased the Pythagorean theorem that I did for this other problem, but I'll put it back up there because what it said was A squared plus root 2 squared equals 5 squared. So notice how here I was solving for C, okay? And so it's important that that's over on this side, right? Here the 5 was C. Again, I'm just reiterating this aspect of the Pythagorean theorem. I often see students just take whatever two values are available and throw them in there for A and B. You really need to understand the difference between the values for A and B and the value for C. C is always the hypotenuse, which is always the longest side of the triangle and is always across from the right angle. All right, let's look at a couple more of these. Problem 6. So here we've got one side of 27. There's our angle theta. This side down here is 36. And so again, we need to use the Pythagorean theorem. And I think I'll need a calculator on this one. 27 squared plus 36 squared equals C squared. I think that's going to come out to be 45. I'll talk about that more in one second. But let's go ahead and calculate this. 27 squared, 729, 36 squared, 1296. So c squared is going to be 729 plus 1296, which is 2025. So c is the square root of 2025. Now I've been leaving it that way for most of these problems because 58, like in this problem, 58 is not a perfect square. But if you square root 2025, yeah, this is a whole number. This is 45, which is what I just said a minute ago. Now the question is, how did I know that without really doing any calculations? So let's take a break here in the middle of problem 6, and let me talk to you about something that are called Pythagorean triples. And these are groups of whole numbers that satisfy the Pythagorean theorem. Okay? One of them is 3, 4, 5. 3, 4, and 5. So 3 squared plus 4 squared equals 5 squared, right? 9 and 16 will be 25. All right? So anything that is in the form 3, 4, 5 will also satisfy the Pythagorean theorem, right? So you could have a 6, 8, 10 triangle, okay? And those values will satisfy the Pythagorean theorem as well. You could have a, let's see here, a 9, 12, 15 triangle. And those values will also satisfy the Pythagorean theorem. As long as everything is some multiple of 3, multiple of 4, multiple of 5, then it's going to fall into this kind of situation. And that's what I recognized here. This is 3 times 9. This is 4 times 9. And so without doing any calculations, I knew that this was going to be 5 times 9. Okay? So that's one Pythagorean triple, is the 3, 4, 5. What else do we have? There's the 8, 15, 17 triple, 8, 15, 17, and any multiples of those, so 16, 30, 34 also work. Oh, 5, 12, 13. 5, 12, 13 is another Pythagorean triple. So 10, 24, 26 also works, and 15, 36, 39 also works. Any multiple of these numbers. But these are the first 3 Pythagorean triples that I know of, and sometimes they do come in handy to save you a little bit of calculation, but it's not something that we're going to spend a whole lot of time on during the term. So I just want to take a few minutes to talk about it right now. Okay. So now that we've got the values for these sides, let's go ahead and calculate the sine, cosine, and tangent. So let's see here. The sine is going to be the opposite, 36, over the hypotenuse, which is 45. And then, of course, since these are both multiples of 9, we can reduce it. This will be 4 over 5. And if you're partial to decimals, then that's going to be 0.8. Let's see, cosine then is going to be 27 over 45, and so that's going to be 3 over 5, and you can call that 0.6 if you'd like. And then the tangent is going to be 36 over 27, which is 4 over 3. And that one's a repeating decimal, so if you want to write it as a decimal, be sure to put that bar in there. Let's see. One thing I'm going to point out here at this right now is the sine and the cosine are always less than 1. Okay? I should say less than or equal to, but they will never be greater than 1. Why? Because the hypotenuse is always the longest side, so it will always be longer than either one of these opposite or adjacent sides. So therefore, when you calculate opposite over adjacent, this is always smaller than this one, so this ratio is always less than 1 if you're working in a triangle. The same thing is true of the adjacent. You can see with the tangent, the ratio of these two sides really can take on any value. Let's see here. Yeah, once we move outside of the right triangle, we will see that sine and cosine can take on a value equal to 1. And I was just about to say, but never greater than 1. But actually, if you open up, our number system to complex value numbers, you actually can have sines and cosines of angles being greater than 1. So, it all depends on what you're using it for in the end. So, let's see. Let's keep going with these. Problem 8. Here's our triangle. There's our angle theta. There's our right angle. Hypotenuse is 8. This side is 4 square root 2. And so now let's set this up and see if we can calculate a value for this side over here. You can call it B if you want. It doesn't really make any difference how you label these, except that C has to be the hypotenuse, and that has to be the longest side in the right triangle. All right, so now we'll say A squared plus 4 square root 2 squared equals 8 squared. So A squared is going to stay the way that it is. This will be 32. So you can distribute an exponent across multiplication, right? You can say x times y squared is x squared times y squared. But you cannot distribute an exponent across addition or subtraction. It just fundamentally doesn't work. X plus y squared has to be distributed, and that'll give you x squared plus 2xy plus y squared. Okay? But you can do this distributing over multiplication or division, and that works just fine. And so I did 16. Square root 2 squared is 2. 16 times 2 is 32. You can also do that on your calculator. 4 root 2 squared should give you 32. This will be 64. Subtract the 32 over. A squared is 32. And so A is square root 32, which, if you go back and look at this, you can see is 4 root 2. Okay, so now we need to calculate sine, cosine, and tangent. Sine theta is going to be 4 root 2 over 8, which is square root 2 over 2, right? Those cancel. Cosine theta is actually going to be the same because the adjacent and the opposite sides are the same. So this is again going to be 4 root 2 over 8, which is root 2 over 2. And then the tangent of theta is going to be 4 root 2 over 4 root 2, which is equal to 1. The angle theta here is 45 degrees. All right, this is an isosceles right triangle where this is 90 and each of these angles is 45. And that has some special values for sine, cosine, and tangent. All right, let's see what else we've got in this section. Okay, let's look at the second part of this on page 20. We'll look at problem 12. And the information we're given there, sine theta equals 3/4. Sine theta equals 3/4. So we can make a triangle. Let's put our theta down here. Then that would be 3 and that would be 4. Okay? So we need to find the third side in the triangle. So we'll say a squared plus 3 squared equals 4 squared. Now, if you're thinking to yourself, didn't we just talk about 3, 4, 5 triangles, and why shouldn't this a be equal to 5? Because this goes back to the idea of C always being the hypotenuse, and A and B always having to be less than C. Okay? In a 3, 4, 5 triangle, 3 and 4 are the legs of the triangle. 5 5 is the hypotenuse, it's the longest side, and those values will satisfy this equation. Over here, notice that the 4 is the hypotenuse. That means A can't possibly be 5, okay? And so we can calculate the value for A. This will be A squared plus 9 equals 16. Subtract the 9 on both sides. A squared is equal to 7. And so A is going to be square root 7. Okay. All right. Well, now that we know that, we already know the sine is 3 over 4. So that means the cosine is going to be square root 7 over 4. And the tangent is going to be 3 over square root 7. And I'm fine if you want to leave this like this. I know that a lot of textbooks and some instructors as well make a big deal about not having a square root in the denominator. But that kind of version, I think, is becoming less and less important. It comes from the days where people had to do calculations themselves, and doing 3 divided by the square root of 7 is kind of taxing, whereas if you can set this up so that you've got something nice to divide by in the denominator, it works a lot more easily. We don't really have to worry about that at this point because we have calculators. All right, let's do a couple more of these, see what they look like. Problem 14, tangent theta equals 2. Which means as a ratio, this is 2 over 1. I mean, that's the key, is that each of these trigonometric ratios represents 2 of the sides, and then you can find the third side using the Pythagorean theorem. Well, in the original problem, we only had a single value. Well, to make that work, you just throw in a 1 in the denominator. Now we do have the 2 sides. We have the side opposite and the side adjacent, right? Let's see, I'll put theta up here. So the side opposite would be 2, and the side adjacent would be 1. Okay? So now we can set up our Pythagorean theorem. 1 squared plus 2 squared equals c squared. So that means c squared is equal to 5, and c is square root 5. Okay. Well, now that we know that, we can find the sine of theta, which is going to be 2 over square root 5, and we can find the cosine of theta, which is going to be 1 over square root 5. And again, we can leave that square root 5 in the denominator. If you're uncomfortable with that, you can do whatever you'd like. You can make these, you can rationalize your denominators. I would hesitate to approximate these as decimal values for right now. We will do a lot more of that, but for right now, let's hold on to these exact values. All right, problem 16. Let's see here. We've already done the sine. Let's see here. We've already done a tangent. Let's do problem 20, where we've got the cosine given to us. So cosine theta is 3 over 7. So let's look at our triangle. So there's theta, and you can put theta here, you can put theta here. It doesn't matter, okay? What matters is that you put the adjacent, opposite, and hypotenuse sides correctly. Once you've chosen which angle you want to be theta, then it's important to recognize 3 will be the adjacent side, 7 will be the hypotenuse. Let's find out what the other side is. So a squared plus 3 squared equals 7 squared, 49. So a squared is 40, and a is the square root of 40. We can leave it like that if we want to. You can simplify this. This would be 2 square root 10. I'm not going to make a big deal about that in this class. Again, it's sort of hanging around from the days before calculators were widely available. All right, so here's our square root of 40. So we've got the cosine. We need the sine of theta then is going to be square root 40 over 7. and the tangent of theta is going to be square root 40 over 3. Okay, let's see what else we've got in this section. That was problem 20. Problem 22. It's kind of interesting. Here we've got the tangent of theta given to us as 1.5. Okay. Well, let's, since this is the last one, let me take some time and go through a couple different ways of doing this problem, which will hopefully give us some insight into something else that's going on in this section as well. All right. Well, what if we want to think of this as 3 over 2? Because that's equal to 1.5, right? Okay. So then we can have a triangle. I'll put my theta down here. Opposite will be 3, adjacent will be 2. Okay. Well, what if somebody else looks at this and says, oh, tangent of theta is 1.5. Well, didn't you just say, take that 1.5 and put it over 1? And then you'll have two sides, right? And I'll make my triangle look very much the same. Here's theta, there's the right angle, and now this will be 1.5 and this will be 1. Huh. Looks like I've got two different situations here. How is this all going to work out? Well, let's calculate. Let's find the value of c in this one. So here we'll say 2 squared plus 3 squared equals c squared. So 4 plus 9 is 13. C is the square root of 13. Okay, all right. What about over here? Over here we would say 1 squared plus 1.5 squared equals c squared. So this is 1 plus 2.25. So this is 3.25 equal c squared. So that means that c is going to be the square root of 3.25. Okay. So, now, over here, we've got all three sides. So if we want the sine ratio, sine will be 1.5 divided by the square root of 3.25. And the cosine ratio will be 1 over the square root of 3.25. Okay? Over here, our sine ratio is the opposite side, 3 over the hypotenuse, which is square root 13. And the cosine there is going to be 2 over square root 13. Now, you might think that these are different answers and that there is some, some miscalculation or something that is not reconcilable between these two. That's not true. If you take these, now this is the benefit of, decimal approximations. Now we could do some, renaming and put this in fraction form and so forth, and we would end up showing that maybe I'll do that after I do the calculator. But let's look at the calculator first. Okay, this one says the sine of theta is 3 divided by square root 13. Okay, and that comes out to be about 0.832. Over here, it says 1.5 divided by square root 3.25. And here we go. I'll show you what the calculator is showing us here. And there it is. They're exactly the same thing. And we'll do the same thing for the cosine. 2 divided by square root 13 versus 1 divided by square root 3.25. And those are both about 0.5547 or so. Okay? So they do come out to be exactly the same. And so what is true there is that even though a triangle might be a different size, your angle can be the same angle and have the same sine, cosine, and tangent. What am I saying there? Let's see. I'm going to have to make some room. And this is a drawing that you may have seen before, may not, might see it in the future, might not. But this is fundamentally what's happening. So here's your angle theta, and you can draw all of these similar triangles like this. Okay? This angle theta is the same in every triangle. Let's see, how many do we have? 1, 2, 3, 4, 5. We've got 6 different triangles, but they all involve a right angle and the angle theta, which means that this angle up here is also going to be the same. And if you remember your geometry, then these are parallel lines cut by a transversal, and these are corresponding angles that are all equal to each other. Okay? So what's happening here, what I'm saying is that, let's say, just for argument's sake, that this is 3, 4, and 5. Well, this one out here might be 6, 8, and 10. Okay? So they're multiples. The sides are multiples of each other. And that makes the sine, cosine, and tangent the same. Okay? Because let's say you do the sine of theta here as 3 over 5 and the sine of theta here as 6 over 10. Well, they're the same thing. Okay? So that's something that's going on with the calculations of the trigonometric ratios, is that even though triangles might be different sizes, their angles will be equal to each other. That's actually the definition of similar triangles, is that triangles that have the same angles but different side lengths are similar to each other. Well, if you've got similar right triangles, then their sine, cosine, and tangent will always be the same. All right, well, I think that's, I've gone on long enough for this section. This was a good introduction to the trigonometric ratios. We'll continue working through the textbook, and we will eventually end up looking at some applications of this. As always, if you have any questions about any of the ideas that we've covered or any of the problems, please let me know. Thanks.